Okay, let's get started. So, last time we spent some time looking at examples of functions that were not continuous, just to kind of build some intuition on what a continuous function is, and also to see some examples where the answer to whether or not the function is continuous at a specific point is not super obvious. And so we need better technology in order to address this question of whether or not functions are continuous. And the first piece of technology that we need is called a collapsing collection. So today I'll start by giving you the definition of a collapsing collection, and we'll see a bunch of examples. And then at the end, we will start giving you some statements that will help you prove whether or not a given thing is or is not a collapsing collection. So let me just start with the definition. So a collapsing collection this is a list, an infinite list of intervals satisfying two conditions. So the first condition is that every interval is contained in the previous one. So the intervals are getting smaller and smaller. And then the second condition is that there is at most one number that's contained in all of the intervals. So I'll write that down and then we'll dive into it a little bit deeper. So there is at most one number contained in all of the intervals. Okay, so what are sort of the possibilities here? So if you have a list of intervals where each interval is contained in the previous one, the intervals could be sort of like shrinking towards one of the endpoints. And in that case, you would have that there's no number contained in every interval, right? Because you can always like sort of shrink the right endpoint far enough that you're missing the point that you thought of. The other possibility is that they're like sort of shrinking simultaneously around one point. And in that case, you will have that one number, whatever is in the middle, that will be contained in all of the intervals. And the other thing that could happen is your intervals could be shrinking towards the endpoints could be shrinking towards one another, but they sort of like slow down at some point, and then there's an entire interval that's contained in every interval. And that's what we're trying to avoid with this second condition, right? So we're going to have either 0 or 1 numbers contained in all of the intervals. Okay, so I'll start with an example. So we wrote down this example last time. So we'll just check that this is a collapsing collection. So let's look at the list. So we'll have the interval from 2.9 to 3.1. And then the second one in the list will be 2.99 to 3.01. The third one will be 2.999 to 3.001, and so on. So you just continue the list following the pattern. Okay, so is this a collapsing collection? Let's just check the conditions. So just looking at the definition, a collapsing collection is an infinite list of intervals satisfying some stuff. We have here an infinite list of intervals. And we need it to satisfy first that each interval is contained in the previous one. So is that true in this case? Yeah. So how can we see this? Well, the left endpoints are getting larger and larger, right? And the right endpoints are getting smaller and smaller. That means that our intervals are contained within one another. Okay, and then the second condition, there is at most one number contained in all of the intervals. Okay, so is there a number that's contained in all of the intervals in this case? Yeah, what is that number? Yeah, so 3 is for sure in all of these intervals, right? No matter how many 9s I tack onto the end of 2.9, 3 will still be bigger than that. And also, no matter how many zeros I stick in here, 3 will also be less than that. So 3 is always whatever, you could go out to the millionth interval in this list and 3 is still inside of that interval. Yeah.
Why is it at most one? Technically for the first one, there could be like 3.001, and that would still be a number in that.
Yes, but 3.001 won't be in all of the intervals, right? So I could take like the 5th interval or something, and 3.001 won't be in that interval, right? So yeah, so is there another number that's in every interval? No. Maybe it's harder to argue why this should be true. So let's take a moment to say, like, why is 3 the only number in all the intervals? So I think so maybe I'll draw a picture. So this is like a really zoomed in picture. So here's like 3, and then I'm gonna just draw this interval in pink, this one in red, this one in green. So here's 2.9 to 3.1. And then the next interval is a bit smaller. And then the next one's even smaller. So the idea here is that, so let's say I pick a number that's different from 3, but maybe it's very, very close to 3. So let's say this is the number that I want to look at. So let's call this one A. So there is some distance between 3 and A, right? There's some positive distance here, which is just given by 3 minus A, the absolute value of 3 minus A. So that means that in order to find an interval that doesn't contain A, I just need to look out far enough in my list so that the width of that interval is less than 3 minus A, right? So I just need to pick whatever interval only will start to exclude A, and that will show that A is not contained in all of the intervals. Does that make sense? So to sort of argue this, we could say 3 minus A, that number will have some decimal expansion, right? So say it's non-zero at the 100th decimal. Well, then that means that if I go out in my list to a place where this right endpoint has 101 decimals, then A will be excluded from that interval. Okay, so that's the idea, is that eventually we'll be able to find that interval that excludes A. Okay, are there questions? Yeah.
So, seemed like before, you're, you're describing a case where it converges toward one of it first interval as being a case where there's a number that's common to all of them. Did you have a case though where it's moving toward the other endpoints of the initial is number and like it's closed of an interval, so it's like
Yeah. Yeah, exactly. Yeah. So we will maybe in like 10 minutes, we'll run through like sort of some different scenarios of like what happens if the interval is closed, infinity, etc. Like, because we had all those different types of intervals. And any of those can form valid collapsing collections. So we'll run through that. Good. Are there other questions? Yeah. That's a good question. So this is gonna give us like a more formal way to talk about like limits and continuity. Because like to look at some like so one of the things we were talking about last time was like to decide whether or not the function is continuous, we want to be able to zoom in, right, on whatever number we're worried about is the function continuous here. And so this is just setting up the framework for like how do we like formally describe that zooming in process. Yeah. Are there other questions? Yeah, another question.
So like to zoom in, so this is sort of the set that this is the process of zooming in. So it never actually zooms into the number 3, but I mean, but sort of infinitely goes into that.
Yeah, so you can think of these intervals as like your windows. So yeah, so like if you're looking at the green interval, then you like zoom in so that that's like the green interval is like your whole world. Yeah, and this will just let us, you know, zoom in as close as we want. Yeah. Yeah, I feel like today is like a step up in terms of just like the abstraction and complexity from the previous lectures. So if you guys have a lot of questions, like I think that makes sense. Yeah.
How would they answer that?
Yes, we'll get to that. Yeah. So, okay, so what are we gonna do? We're gonna, and they'll have example problems on the web work today too. But so what we're gonna do now is I'm gonna give you a few standard collapsing collections, and we'll make an argument as to why those are collapsing collections. And then we'll get a couple of tools for like creating new collapsing collections from old ones. So like a sample exam question, I'd be like, is the following list of intervals a collapsing collection? And then you'll have like various tools to define whether or not it is a collapsing collection. Okay, so there's two like standard collapsing collections. So let's talk about those. These are the standard collapsing collections. And the first one is using decimals. Oops. Okay, so it's going to be very similar to this example where for each interval, so say my favorite number, in this example, my favorite number is 3. We're making our collapsing collection to be one that contains the number 3. So I'll start by, in the first interval, subtract 0.1 for the left endpoint and add 0.1 for the right endpoint. Next interval, we'll do 0.01. The interval after that will be 0.001. So that's the idea behind the standard collapsing collection using decimals. So here's how it will look. So let's let A be any real number. So in the above example, it was 3. Okay, then the standard collapsing collection using decimals for A would look like the following. So we're going to do A minus 0.1 up to A plus 0.1. Next one, A minus 0.01 up to A plus 0.01. And then the third one would be A minus 0.001, A plus 0.001. And then the pattern continues. So this would be our standard collapsing collection for A using decimals. Yeah, do you have a question?
Oh, yeah, there wouldn't be another one besides this, right?
Um,
Is that just drawing?
How do you mean?
Like, you're saying like using decimals, like, is there another way to write?
Yeah, so the second like standard one will use fractions, and so it'll be like subtracting a half, subtracting a third, a fourth, etc. Yeah, so maybe I should just write the second one now. So here's the one using, and they say reciprocals, so. So yeah, here's the other one. So it would be A minus 1/2, A plus 1/2, A minus 1/3. Oh, you know what? I think they actually start at 1. So let's do that too. And then the third one would be A minus 1/3, A plus 1/3, and so on, continuing in that way. So this is the standard collapsing collection. For A using reciprocals. Okay, so these are sort of the two standard ones that will be sort of like a starting point to find other collapsing collections. Are there questions about these? So maybe now is a good time to say when you have an infinite list of things like this, it will be useful to be able to speak about an arbitrary element in this list. So like maybe I want to talk about the 100th one, or for like an arbitrary number, you might just say like the kth element of the list. So here's how that would look. So I'm going to shrink this a little bit to make space on the right. Okay, so the kth element, the kth interval. So how would that look like? So we have to decide, we have to kind of see what the pattern is. And then that will tell us what any interval in this list will look like. So the first one, well, I wrote this maybe in a bad way, but you can think of 1 as just being 1/1. So the first element in the list deals with 1/1. The second one deals with 1/2. and the third one deals with 1/3. So the kth one in the list will deal with 1/k. So we can write down that this will be a minus 1/k up to a plus 1/k. Does that make sense? Are there questions about that or how I figured that out? Yeah,
How would you describe the K interval for the decimal
yeah, the decimal one's a little bit trickier, right?
K number? Power.
Yeah, so that's exactly right. So, right, so to do this one, I'm gonna rewrite these as 1/10 to the something. And that will make it more clear what the pattern is. So I need more space, so I'll just start over down here. So the kth interval for the standard, I'm gonna abbreviate collapsing collection CC using decimals. So here's how that would work. Okay, so I'm gonna rewrite the intervals using powers of 10 rather than decimals. So this would be a minus 1/10 to a plus 1/10. Second interval is a minus 1/, so this would be 1/100, which is 10 squared, up to a plus 1/10 squared. And then the third one is a minus 1/10 cubed, up to a plus 1/10 cubed, and so on. So the kth one would be a minus 1/10 to the k, just because in the first one I had 10 to the 1, and then I have 10 to the 2, and then I have 10 to the 3. So the kth one will have 1/10 to the k, up to a plus 1/10 to the k. I feel like this green color is coming up a little bit like neon on the screen. I'll change it later. Okay. Okay, so those are the two like standard collapsing collections. And we will prove later that these are collapsing collections, right? Because so far I have not really argued to you why these two things actually satisfy this definition, right? So I should, if I'm going to say these are collapsing collections, I should provide to you a convincing argument that these two lists of intervals satisfy these two conditions. So we'll do that in a minute. Are there questions about these? Okay, so now we'll get to the issue that you raised earlier about the endpoints. Like, what if they're closed, or what if it's an infinite interval, things like that. So here's like 4 types of collapsing collections. And these really just depend on the types of intervals appearing in your lists. So the ones that we have looked at so far are called two-sided open collapsing collections. And you would say that it's a two-sided collapsing collection for a number A if A is contained in every single one of them. So if I say for A, that means that A is an element of every interval. Okay, so, here's an example, so the minus 1, 1, minus 1/2, 1/2, minus 1/3, 1/3, and so on. So this is an example of a two-sided open collapsing collection for 0. Okay, so that's the first type. The second type is, we could have closed. All right, so why is this called two-sided? So this is, sort of what I was getting at earlier, but, there's shrinking happening on both sides. So we'll have a one-sided version where you leave one side alone and only the other side is, shrinking. So this is that's what the two-sided means. Okay, so closed collapsing collections for A. So this would just mean that your intervals themselves are closed. So here's an example of a closed collapsing collection for 0. This is a closed collapsing collection for 0. Okay, and then we have the one-sided collapsing collections. So let me write down an example. So could have something like 0 to 1, 0 to 1/2, 0 to 1/3, and so on. Okay, so this one's kind of funny because there's no number that's contained in all of the intervals, right? Let's think about that for a second. So 0 is not contained in any of the intervals, right? Because the left endpoint is, we have a parenthesis there, so that means there's a closed interval on the left-hand side. And then, since these right-hand sides of the interval are shrinking, no matter, so if I picked a number that I thought might be contained in all of the intervals, like 0.000001, something like that, I will be able to find an interval that does not contain that number because this is getting closer to closer to 0. Okay, so these don't contain any number, but we still say that they are a collapsing collection for, or sorry, we say they're a one-sided collapsing collection for 0 because 0 is sort of what they're shrinking towards in an intuitive sense. So if you have one side of your intervals the same always, then that's a one-sided collapsing collection for whatever that that number is. So excuse me. This is a one-sided collapsing collection for 0. And I'll just make a comment that no number is contained in all the intervals. But we just call it a one-sided collapsing collection for 0 because 0 is the left. Okay, so Of course, like these come in two flavors, right? You could have, the left endpoint of the interval being the same number every time, or you have the right endpoint of the interval being the same every time. So you would just call that a right-sided collapsing collection versus a left-sided collapsing collection. So here we have like a distinction between right versus left. Okay, and then the last type of collapsing collection. Oh yeah, do you have a question?
If the whole point of like this collapsing collection is to like do continuity, and on a one-sided collapsing collection, if the number itself doesn't even have to be in within it, then how is that showing continuity if it's like not there? You know what I'm saying? So like on a graph, since it's a, you know, currency is just like be open. Like with that shows this like a whole continuity.
So this will come up more when we're dealing with limits, because you might wonder what the limit is coming from one side versus the other side. Yeah. So we're gonna use these for more than continuity. Other questions? So another one, so this last type is also mostly gonna be for limits and not really used in continuity, but this is collapsing collections for infinity. And this could be positive or negative infinity, so I'll just write plus or minus infinity. So here's like an example. So something like 1 comma infinity, 2 comma infinity, 3 comma infinity, and so on. So again, there's no number here that's but since infinity is the right endpoint in there, you say that that's a collapsing collection for infinity. Okay, so this was a lot. Are there questions? So now we've sort of set up like what is a collapsing collection, and we've seen a couple of examples and some different types of collapsing collections. So what we're gonna do now is set up some tools to make rigorous arguments about collapsing collections. So there's gonna be several facts that we'll use. So the first one, let's see. So here's our first fact about collapsing collections, which is that the standard collapsing collection using reciprocals is in fact a collapsing collection. And I'll say, let A be a real number. Using reciprocals is a collapsing collection. Okay, so earlier I just gave you a list of intervals and said we're going to call this thing the standard collapsing collection using reciprocals, but we actually need to say why does this thing satisfy the definition of being a collapsing collection. Okay, so what do we need to do? So let's go back to the definition. Okay, so we said that a collapsing collection was an infinite list of intervals satisfying some conditions. And the first one was that each interval is contained in the previous one. And the second is that there's at most one number contained in all of the intervals. Okay, so let's grab our standard collapsing collection using reciprocals, and then we have to prove those two claims. Okay, so what we need to show, I'm just gonna keep tally of this. We need to show the two properties. So first, every interval is contained in the previous one. And the second is that there's at most one number in every interval. Okay, so I'm going to write a proof of this fact. And here's sort of how the notation for proofs goes. So you start by writing proof on the left. And then what you need to do then is to write a convincing argument for why the fact is true. So, you know, like what counts as a proof, I think is like sort of open to interpretation, right? Because it depends heavily on who your audience is, right? Like an argument that is convincing for one person may not be convincing for another person. And this is like a real live issue that comes up in math. So for example, there's like famous long-standing conjecture and someone has claimed to have solved it, but no one can understand the proof. And so there's sort of like a philosophical question of like, well, is the conjecture solved or not if, you know, only this one person can understand what is written here, right? So, but our job in this class is just going to be to write an argument that's convincing for us as to why the fact is true. So usually started off by just writing this, and that just indicates that right now we're going to make an argument for this. Okay, so then, and I'll say like, you will be expected to write arguments like this and justify claims and things. Okay, so let's let A be a real number. Then what is the standard collapsing collection for A? So then we're considering so I have it in my my clipboard. So this is the standard collapsing collection using reciprocals. So the standard collapsing collection for A using reciprocals. Okay, so we need to argue these 2 points. So first, why is each interval contained in the previous one? So often, it can be helpful to just write down exactly what we're claiming. So I'm going to write down the kth interval and the one that comes after it, which is the k plus 1th interval. And we're going to compare them. So our claim is that the kth interval was a minus 1 over k to a plus 1 over k. And the next interval was a minus 1 over k plus 1 up to a plus 1 over k plus 1. Okay, so those are the 2 intervals that we're comparing, and we're saying that the k plus 1th one is contained in the kth one. So that's I don't know if we've seen this symbol yet. This is the backwards of the subset symbol, which is like superset. But anyways, it just means that this interval contains that one. That makes sense? Okay, does the claim make sense? And does it make sense why this is what we need to show? Right, because if this is true, then that means that every interval is continuing the previous one, right? We're just gonna, so basically what this is doing is like, we're taking an arbitrary interval and the one after it and comparing them. So if we argue that this is true, then it follows that every interval is continuing the previous one. Okay, so why is this true? Yeah.
This element in both sets. And then make sure that if one is larger.
Yeah, so we can start by just comparing the left endpoints and see, right?
Oh, and then also like compare within the set to make sure like one's different. Like both the endpoints and then.
Okay, so let's go like fully in the weeds with this, right? I think this is what's gonna make the most sense. So going back to when we defined intervals, right? Who is in this interval? This is the set of things that is between two numbers, between these two numbers. So let me just write this out as a set. So a minus 1 over k, a plus 1 over k. Okay, so this is the set of real numbers x such that a minus 1 over k is less than x, which is less than a plus 1 over k. Okay, then this other interval is a minus 1 over k plus 1 to a plus 1 over k plus 1. And this is the set of, I'll just call these y's just to make it less confusing. So this is going to be the set of y's in R such that a minus 1 over k plus 1 is less than y is less than a plus 1 over k plus 1. Okay. So what we need to do in order to show that this set is contained in this one is I need to take any element of here and show that it is also an element of here. Does that make sense? So basically I need to take a real number that satisfies this set of inequalities and show that that real number then also satisfies this condition, these other inequalities. Okay, so that's our game plan. So let's let y be an element of this second interval. Meaning that y satisfies these inequalities. Okay, then we need to show that y satisfies this inequality and that y satisfies this inequality. So then, so I'll do the left one and then you guys can do the right one. So we know that, so let's compare 1 over k and 1 over k plus 1. Which one is bigger? 1 over k is bigger, right? So like with this kind of thing, I feel like sometimes I get mixed up about reciprocals and all that. So it can be easier to just think of an example. So sidebar, like we're comparing something like 1/2 and 1/3, right? And 1/2 is bigger. So the inequality points this way. Okay, then that means that if I look at A minus oops. Let's now compare these two quantities. Which one is bigger now? Yeah, this one is bigger, right? So again, like sidebar, if I set A equal to 1 or something, 1 minus 1/2 versus 1 minus 1/3, right? The right one is bigger. So we have that. Okay, and now we're happy because we know that y is bigger than this thing. So that tells me. So I have this inequality that we just argued for. And we already know, because y came from that interval, that y is bigger than that. So that means that y is bigger than a minus 1 over k. Feel like maybe we're like maybe too in the weeds and we've lost the train of thought. So right now I'm arguing for why this inequality is true. So that's this argument. Is that making sense? So now we're like halfway to showing that y is an element of that top interval. We would just need to prove that the other inequality is also true. So let's do the pink inequality. Okay. So why is this one true? Okay, so part 2. So this was all, let me just like label this so it's a little bit clearer. So this is showing a minus 1 over k is less than y. Okay, so now we want to show that, so part 2, we're going to show that y is less than a plus 1 over k. Okay, so why is this true? I feel like we went really deep with the blue inequality, so maybe now we're like more prepared for the pink one. So how does a plus 1 over k compare to a plus 1 over k plus 1? Which of these two things is bigger? Left side. Okay, good. So we have the inequality pointing this way. Do you agree with this? Then we already know, because y came from the little interval, that y is less than this. So this is by right? So that means that y is in fact less than a plus 1 over k. So what have we concluded? That means that y is an element of a minus 1 over k, comma, a plus 1 over k, which means that this interval, a minus 1 over k, comma, a plus 1 over k, contains a minus 1 over k plus 1, comma, a plus 1 over k plus 1. Okay, so we went, really deep with this. I think in the future, you could, if you're comparing two intervals, you could just compare the two endpoints. Right, so say, so like, let's just draw a picture. So let's say I'm comparing the blue interval and the red interval. Well, if the left endpoint of the red interval is bigger and the right endpoint of the interval is smaller, then the red endpoint is contained in the blue endpoint. Or sorry, the red interval is contained in the blue interval. Okay, so where are we at in this argument? So we proved the first property. Next time, we will look at the second property and give sort of more tools for dealing with collapsing collections. Yeah. Yeah.